Okay, the other day I showed some measurements of my replication of a fleet generator, and there's my little boy down there. I'm going to do some more stuff today. I thought you'd might like to see some of the things, the other measurements I take with this. It's kind of interesting. First, a little history is I started out with this toroid. This whole circuit started out being a jewel thief, something I found on the internet. And this only has 11 bifilar windings on it. It's 11 double loops, or two pieces of wire side by side 11 times. And it worked. It worked quite well. So I did some research on where the jewel thief came from. And it came from a magazine article in 1999, and it has kind of cult status because you can take very, very dead batteries and get a little more use out of them. So I looked up Lawrence's information, and I made a much bigger coil, as you can see on this guy here. This has about 80 to 84 winds of very, very good magnet wire, which is a high conductive wire with a very, very thin insulation on it. So like most of these circuits that I've built, basically the bigger the coil, the better. And I tried it with this, and it works really well. Now you can see that in the past, when I had my smaller, see the 50 volt marking right there? I had the smaller toroid coil on there, and I was able to get about 50 volt peaks out of that. And now I can get much higher peaks because I have much more windings on that coil. I think when the magnetic flux in the coil collapses, that's where you get your energy from the environment. I think the more wire you have there, it's like putting up a bigger antenna to catch more outside energy. When the field collapses, it goes rushing in. And I just think the more area you have, the better. So far, that's been working out. So today, we're starting with the same old battery I've been using. And it's coming in right now at 1.260. So the battery is just getting a little bit weak, but there's plenty of juice for this circuit. It only needs I think I read it can still work with less than half a volt in the battery. So let me set this guy aside. I just wanted to show you how much power this thing outputs. It's actually rather astonishing. So let me just take these guys off of here. Oh, pardon me. Didn't mean to bump you. I'm hooking up the battery with my little Band-Aid system here. I don't have a holder for a single battery. There you go. Now you can see that of course the LED is lit. That's the basic circuit runs an LED just so you can see there's something going through it and know that there's more energy going into the LED than this single battery can put out. Because this particular guy needs 1.85 volts to just light, no less be bright. It takes about 5 volts to make it bright. I wanted to show how much energy is in this electromagnetic flyback when that field collapses. It's huge. Just in comparison, a normal transistor, this little tiny guy, it's a real tiny transistor. It's a very weak transistor. I got it for 10 for $1 at Electronics Gold Mine, and that's capable of traditionally, in a traditional circuit, it can amplify up to 30 times. So if we had a 1.3 volts we're putting into the circuit, that would be about 23 volts coming out. Okay, so let's take a look. Right now, again, I have this meter connected to the circuit through a little tiny diode because I need to rectify the circuit down to DC so I can measure it, and I slow it down with a tiny 0.1 microfarad capacitor, again, to make it DC, because this circuit is actually pulsing very, very fast. So I'm going to take the light out of the circuit, and I want you to watch the meter over there. I know you can't really see it where you are. Let me move slightly. You can't really see the meter, but it's on a 60 volt scale. Let's see if I can get down there. I know this gets a little blurry when I put it up to the internet. It says 60 volt DC scale. Okay. And right now it's showing just a little bit on the dial. You can see the dial's not at 0. And what I am going to do is just flick off the light and watch the dial. Bam! Just pegged itself. You saw that, right? So, pardon me. It's hard to do camera work on this at the same time. So, I'm pegged over 60 volts. Now, I want to explain. Put the light on and it drops back down to 4 or 5 volts because the LED is now consuming some of the energy. I just like to explain that the circuit pulses, so you get a very high peak and then a period of rest. So you're getting pulsing DC, which makes taking measurements extraordinarily difficult. It's not AC particularly, and it's not actually DC, so a lot of the laws you learn in school don't actually apply to this circuit. This is one of these circuits that they say, oh, don't worry about that, write a doctorate on it, later. So I want to hook this up to my digital meter. I'm going to change the range of my digital meter up to hundreds of volts. If you can see where that decimal point is. So it's going to read in the hundreds of volts. Now there's not much power in this circuit, so it's not dangerous. Just one of the nice things about this circuit, it won't kill you because we're using such tiny amounts of power. It's only 100 milliamps at best, so. Come on, baby. And let's see if you can see that. If you can't see it, I'll tell you that it's 3.8 volts, which makes sense with the other day's deal. Let me see if I can prop this up just a little bit so you can see the decimal point. It's 3.8 volts. It makes sense to yesterday's test. It's because the light is running, consuming some of that energy. It's also acting as a diode. Let me take this light off again out of the circuit, and let's see what happens to the meter. Shabam! Did you see it jump? $83.4 volts. Pretty steady. 83.3, 4, 3, 4. Very good. So I don't have an oscilloscope, but using this method, I'm assuming that I'm getting 83 volt peaks, and then a period of rest and a peak again. And so that is a lot of energy coming out of a single AA battery. In fact, not even a fresh AA battery. So I think that's pretty incredible. So this circuit is a real winner. I got to do some more tests. I have tested it with larger capacitors. A 47 microfarad capacitor is more dramatic. It takes some time getting up. Not long though. It takes about 5 seconds. And then we have the big jumbo circuit here, filling up a lot of capacitors. And that's very dramatic because you can take the power away and use it someplace else. Unlike a battery, the capacitors charge quick and they'll give you back all the juice. Whereas when you charge a battery, you actually have to give it much more energy to get it charged, and it doesn't give back all the juice. It's actually kind of wasteful. So I just wanted to share that this circuit is very, very powerful. And I wish I could show you on an oscilloscope, but it is powerful, it's useful, because you can use such a small amount of energy and get a high amount of energy back. And it costs almost nothing to make these things. These little toroids, I got a large toroid pack from Electronic Gold Mine, 5 for $1. These little transistors are almost a throwaway item. I got 10 for $1. I got a bag of LEDs. I think I paid $5 for like 200 of them. I mean, come on. And when you touch it, it doesn't tase you. So this is quite fun. I'm having a lot of fun with this, and I'll let you know when I find more developments. I'll let you know what's going on. So this is Ron. See you.